In order to understand higher levels of protein structure, we really need to begin by understanding the conformation of the peptide group. And ultimately, in order to define the conformation of the peptide group, let's look at the peptide bond itself. Remember the C double bond O, bond N, bond H, right? This right here, the C bond end, is the peptide bond. So the peptide group is actually defined as those atoms involved in the peptide bond, but additionally the alpha carbon that binds to the carbonyl carbon, as well as the alpha carbon that binds to the amide nitrogen. Together, this entire group is the kind of root structure or core structure of higher levels of protein conformation. And so this is the peptide group. Now, one of the things that began happening and perplexing scientists was that when they looked at what was this supposed C double bond O, they started to recognize that it was actually slightly longer than a typical C double bond O. So we're going to go ahead and jot that down, recognizing that this was a bit of a eureka moment when they realized that, in fact, this was longer than what you would expect to see if this were actually a kind of true and traditional C double bond O. And likewise, interestingly, the peptide bond itself, the amide bond, was slightly shorter than what they were expecting to see. So this was a little bit further perplexing, but probably hypothesis generating, in that it's a recognition that the true structure is actually going to be something in between the two, the beautiful nebulous in between of a resonance hybrid structure. So I hope you remember from chemistry drawing the two imaginary structures that allow you to get to the resonance hybrid. So this is a recognition that our true structure is a resonance hybrid. And that in fact, if we are to go ahead and draw the two imaginary structures, looking first at the one that we drew above, but then recognizing that additionally this lone pair of electrons can pop down here, and this of course pushes this pair of electrons up onto the oxygen, and we get another imaginary structure in which we have the negative charge on the oxygen and the positive charge on the nitrogen. In actuality, we know that the resonance hybrid is somewhere in between, and I don't know if anyone else was lucky enough to have that fantastic chemistry book in which they talked about a resonance hybrid being kind of like when a purple horse mates with a blue donkey and you get a purple mule. I mean, totally weird and random kind of analogy, but it obviously must have worked because I still remember it. So here's our resonance hybrid in which we actually see a bit of both of these structures being the case, over which the electron structure is delocalized across the peptide bond and across the C bond O. And we get, because of that, a certain amount of character of the right-hand resonance structure in which there's a partially negative charge on the oxygen and a partial positive charge on the nitrogen. This, of course, makes the peptide group itself polar, and it enhances the local neighborhood interactions that we talked about in secondary structure, making those a lot stronger hydrogen bonds between the carbonyl oxygen and the amide hydrogen. So we overall would note that the peptide group is polar. Absolutely. And that affects so much of its bonding behavior. And so we also need to recognize what this does to the nature of the peptide bond, because where we would have once thought that this single bonded nature would make this a very flexible bond around which free rotation was possible, in fact, the fact that this is a resonance hybrid means that really we do not see any rotation. So no free rotation around that peptide bond, as might have been expected if it weren't a resonance hybrid. And that can be contrasted with these other two bonds, the C alpha bond C and the N bond C alpha, around which free rotation is possible. Now let's take a look at this using a model, because that always is way more fun. Due to the partially double bonded nature of the peptide or amide bond, and therefore the lack of free rotation around that bond, we actually can see two different conformations that can form around the peptide bond at the stage of synthesis. Let's pull our attention to this model, back to our good old model, and see the peptide bond. If you take a look here, we can find our peptide bond right here, peptide or amide bond, the carbonyl carbon doubly bound to the oxygen there, and the amide nitrogen here. And of course, this is the bond around which free rotation is not possible. And thus, at the time of synthesis, two different conformations essentially have to be chosen between. So we can think of our peptide bond, because of the lack of free rotation, as being like a plane. And I'm going to show you this plane quite fittingly with a chocolate bar that was just given to me by one of my past biochem TAs. So this is going to be the plane right there. And in this particular conformation that we currently see, we can recognize that the two alpha carbons, right, this one here and this one here, are on opposite sides of the plane. So this is one possible conformation. Now, at the time of synthesis, the other possibility for the conformation that we can see there is the conformation in which both alpha carbons are on the same side, the bottom, in the way that we're showing it, of the plane of the peptide bond. So let's just check that out again one more time. So we have this conformation where both alpha carbons are on the same side of the peptide bond plane, versus this conformation in which they're on opposite sides. These have a very important name. This is the trans conformation. This is the cis conformation. Trans and cis. And I hope that what you're noticing as I make those changes is the large amount of steric hindrance that exists in the cis conformation that is alleviated in the trans conformation. So as you might very fittingly guess, most commonly we totes see the trans conformation as opposed to the cis.
So let's write that down then. There's the two possible conformations. The first, in which you see that the alpha carbons are on the opposite sides of the plane of the peptide group, and we call that, of course, the trans conformation. And then, of course, we've got the opposite conformation where the two alpha carbons of the peptide group are on opposite sides of the plane of the peptide bond. So we know that peptide bond, because of its double bonded character, no rotation, no free rotation around it. So either cis or trans. And what that means is that that is determined at the time of synthesis. So it's not a situation of constant fluctuation between the trans and cis isomers of this around this particular bond. And in fact, for the most part, as we mentioned, the trans is predominant because of steric hindrance. Things are a lot more comfortable if the trans form is incorporated at the time of synthesis, or it's in that conformation at the time of synthesis. So the cis and trans conformations are formed at the time of synthesis and cannot be interconverted by rotation around the peptide bond, because free rotation around that bond is not allowed. Now, there are some exceptions to that. In respect to the fact that sometimes you do see a cis peptide bond. For example, that's often in areas where you see a proline anyway, and the proline's causing a tight turn, and in introduction of the cis conformation at that site introduces little, if any, extra steric hindrance. So you may at times see it there with the kinky proline amino acid. It may also be that you do see an interconversion at times, but this interconversion between cis and trans forms has to be enzymatically catalyzed. And we will actually look at a picture of what's called a peptidyl prolyl cis-trans isomerase, which is the enzyme that can actually interconvert between the cis and the trans forms of a peptide group, right? Okay, great.